Yep. Okay, so this is the first problem we're going to be covering today, CSE Social Distancing. So the idea, or the main idea of this problem is what is the minimum number of seats required to seat n people around a circular table, given that the kth person must be AK seats away from any other person. So this problem was sort of inspired by like COVID and social distancing. So the sample input we've got here, so the first line 3, is n, which is the number of people in the table, and then the next line just contains A1, A2, A3, so the respective distances. So the sample output there is 8, and we've got those constraints and subtasks there. So we've got an example diagram on the next slide that sort of illustrates the scenario. So on that black circle, sorry, there should be another like black point, but I forgot to add that in. So around that black circle, that's sort of the optimal configuration for seating the 3 people there. So person 1 at the blue dot, person 2 at the pink dot, and person 3 at the red dot. And thank you for drawing in that black dot. Yep. So you can see that the blue person needs to be a distance of 3. So you can see that we've got those 2 arcs there representing the distance of 3 from any other person, and then the pink person needs to be a distance of 2 from any other person, and the same for the red person. And this is the optimal solution. So we need 8 people, or we need 8 seats around the table to fit everyone with those constraints. So let's go on to the next slide and see how we can solve this. So it is a good strategy with any problem, not just with programming problems, but even maths problems, to try out small cases by hand. So if we just have one person to seat at the table, then, well, we just need one seat, right? Because he doesn't need, or she doesn't need, to social distance themselves from anyone else. So for n is equal to 1, the answer is just 1. Now, what if we have 2 people? So if we have 2 people, we can just seat the 2 people directly opposite from each other with an equal number of seats on either side of the table. And that number on either side will be the maximum out of the 2 distances A1 and A2. So 2 times the max of either A1 or A2. Now, if we have n is equal to 3, it's not as obvious what we can do. Okay, so you might try that on a piece of paper and try it out for n is equal to 3 and n is equal to 4, but these ones are slightly trickier. Okay, so what we can do is we can try a greedy approach, and we can try a greedy approach first, and then we can think about if we can do any better. If we can prove that the greedy strategy is optimal, then we have solved the problem and we found the minimum number of seats needed. So before I even talk about the actual solution, I'll just mention, I'll use the terms like most sick and least sick and so on to refer to how far away a particular person needs to be from any other person. So that just means, for example, the maximum number in the list or the minimum number in the list and so on. So that's the sort of from the social distancing context of the problem to make it easier to communicate. So the idea is, let's place the person who is the most sick, i.e. the maximum value of AI, on the table. And then the next person needs to be at least that number away from him. So let's put the next sickest person as close as possible to the first person, the sickest person, to sort of utilize as much as possible the existing gaps or the existing seats as much as possible. So we'll try that. So we're going to sort the distances and seat the people around the circle in that order. And that's sort of, if we have so if we go around the circle and count the gaps, that would be the largest gap. Then we have the next person. Then we have the next largest gap, or the next largest value in that list, and then the next person, and then so on. And this continues to go around the circle until we get to the least sick person. And by doing this, this ensures that no extra seats are reserved unnecessarily. So what I mean by that is at every single allocation of the next person, we're not adding in extra seats in between them unnecessarily. So so we're utilizing the existing gaps which have already been created by the previous person, which had to have that amount of space anyway because by the nature of sorting, they had a larger gap already. So this goes all the way around the circle until we get to the least sick person. And then now we have this gap between the most sick and least sick. So if we go back to the previous slide and look at the diagram, we can see that when we go around, we put the blue person in, then we go around 3 gaps to the pink person, then we go around 2 gaps to the last person. But now that last person, the red person, only has a contagious factor of 1. But we can't put him directly next to the blue person because that blue person actually has a contagious factor of 3. So that's the only part of the problem which we need to sort of factor in. But other than that, we've pretty much solved the problem. So we just add up all the numbers. Yep, next. Yeah. Oh, yep. So we just add up all the numbers, the total seats, and that is all the distances, except for the smallest, because instead of the smallest distance, we actually need to replace that with the last gap size, which is actually the maximum out of the list. So that comes from the first person, that blue person. So that gives us this formula, finally. The minimum number of seats, if n is equal to 1, then we just return 1. But if n is greater than 1, we take the sum of all the terms, the sum of all the distances, except for the last person, the smallest term. And then instead of that, we add on the blue person's distance, which was the maximum of A. So that's the formula. And to implement this in either C or Python is pretty simple. So this is a Python solution, just using the standard library functions, sum, max, and min. And that's pretty much it. Someone asked me, private messaged me, could you explain the greedy approach? I am new. The greedy approach, or a greedy algorithm, just means at each point or each selection you're making, you're choosing the optimum selection at each point, which is what we're doing here. So we're allocating the people around the table person by person in order of how contagious they are. Now notice that even though in our algorithm or in our steps we sorted the list, in the actual implementation we didn't need to sort because the sorting just occurs during the allocation step. But when we're actually calculating the number of seats, we actually don't need to sort at all. We just sum up the list directly. And that's pretty much it.
All right. Thank you, Jonathan. I think, should we give about a minute for anyone to ask any final questions?
Would that be possible for you to walk through using the sample input and 3, 1, 2, 3, and output is 8? How would you get that? Can you walk through?
Yep. So this diagram actually corresponds to the sample input and output. So because the numbers are because 3 is a pretty small number still, it's easy enough to sort of just try out all the combinations. There's not many. There's basically you can easily try out all the combinations by hand and sort of just draw what I've drawn, like how I've drawn the two the arcs around each side, sort of just to represent the distances they must be. So when I do this by hand, I would probably put in one person and then draw in the two rays, the two arcs, and then I'll do the same thing for each other person, and then just sort of see if I can like rearrange them or move them around such that there's as much sort of overlap as I can, because I do want to try and overlap as much of the rays, the arcs, so that I'm reusing as much of the existing gaps as I can, rather than introducing new seats unnecessarily. Does that answer your question?
Yes. Yeah. Thank you.
Yeah, there's only like two possible ways you could really arrange them.
All right.
And then even then it's like symmetric, so
Thanks, Jonathan. So the next problem is going to be Honeycomb Explained by Joseph.
All right, okay. Thank you, Turan. Let's get started. Honeycomb. It's a classic mathematical problem. So the problem statement says basically a honeycomb is composed of a collection of cells of the same size. The length of a side of the honeycomb is the number of hexagons that makes up that side. So yeah, we gotta find the number of cells with the side lengths A, B, C, D, E, and F in clockwise order. So actually this problem is pretty simple. Here, the input we have, the sample input we have is 667394, and as shown in the diagram, we can see here that like if you want to count it, the number of cells inside the hexagon or the honeycomb is 81. So yeah, could you go to the next slide now? Yeah, so there's one tip that I want to give, that whenever there's an equiangular hexagon, like all the interior angles are equal, like they must be 120 degrees. Always try to expand sides to form an equilateral triangle. So basically, it's just the way you find an area of a hexagon like this. Yeah. So this will provide you with sufficient information to find the missing lengths. So with this diagram on the right side, you can see it's becomes very easy to solve this problem actually. Yeah. From the figure it can be seen that the number of cells in the honeycomb in the gray area is the number of cells in the big triangle, subtracted by the number of cells in the three red triangles. So yeah, next slide please. Yeah, the length of big triangle, sorry, it's a typo. It's supposed to be f plus a minus 1 plus b minus 1, which is f plus a plus b minus 2. And consecutively b minus 1, d minus 1, and f minus 1 for the right side triangles. So also please mind that all of the triangles are equilateral in shape. Yeah, could you go to the next slide, please? Yeah, so basically the number of cells in a triangle can be obtained from a triangular numbers. So this is the formula, n times n plus 1 divided by 2. So actually the triangle number or triangular number counts objects arranged in a equilateral triangle. So yeah, once again, the triangle we have made is an equilateral triangle. So you basically just want to compute the number of the objects inside the bigger triangles minus the 3 smaller triangles. Yeah, so this is the C code, right? This is pretty simple. You can see using the triangular formula we have the f plus a plus b minus 2, which is the side length of the bigger triangle, times f plus a plus b minus 2 plus 1, which is f plus a plus b minus 1 divided by 2. This is the number of cells in the bigger triangles, subtracted by f minus 1 times f over 2, the number of triangles in the, number of cells in the smaller triangle, and minus b minus 1 times b over 2 in the other right triangle, and finally minus d minus 1 times d over 2. Yeah, that's basically it. Feel free to ask some questions.
Yep, give it a little time for that.
Also, alternatively, for the length of the bigger triangle can be written as b plus c plus d minus 2, or b plus e plus f minus 2. Is just the same. The way you want to see the length of the bigger triangle. Maybe if you are wondering how could someone notice if this triangle, the number of cells in the triangle would require a triangular number formula. There's a good website usually used by many competitive programmers. It's called Online Encyclopedia of Integer Sequences, or OASE.org. So that website basically gives you the name of a certain sequence, some special sequence or anything. So basically, yeah, OASE.org. So basically, you want to do a trial and error, like you make your custom input, like here we have, what if we have like one, what's supposed to be the output, and then we try what if we have 3, what's supposed to be the output, like for example 5 and it's 5, the output should be 15. So then we can just use the website. We put our sequence of integer, and it basically will show our potential answer. So when I did this problem, it immediately gave me that this kind of sequence is called a triangular numbers. So yeah, that's how I found the formula, and that's it.
All right. Thank you, Joseph.
Thank you.
Yep. So the next problem is going to be pair pairs, presented by me. So the problem for pair pairs describes a sequence of n positive integers, and your task is to find the number of distinct ordered pairs of integers that you can make from this sequence. So what do I mean by distinct ordered pairs? Well, so you see from this sequence, we have a 1 to the left and we have a 2 here. So if we were to make a pair out of the 1 and the 2, then this pair here is different from the pair 2, 1. So they're ordered inside the pair. So let's go through this sample input. In this sample input, there are 6 possible ordered pairs of integers that you can make. The first one, let's do all the ones starting with 1. So you can take these two to make 1, 1. You can also do 1, 2. You can do 1, 3. And the elements starting with 2, you can do 2, 2, 2, 3. And starting with 3, you can make the pair 3, 2. So there are 6 pairs in total here. And notice how we can't make the pair 2, 1 because 2 does not appear before 1 anywhere in this sequence. Okay, let's go on the next slide. And I think I'll try and erase. Yep. Excellent. So to count the total number of pairs, what we can do is we can try a simple brute force algorithm, which is just to test every single possible pair of indices in our sequence. Now, for each index I and for each index j after I, we can store the pair AI, AJ, and at the end, we can get all these pairs, gather them up, and then count the number of distinct values through a variety of means. Yep, next one. So obviously, you're going to have to test all n choose 2 combinations of indices. And since n is up to 100,000, this is going to be a total of almost 5 billion pairs, which is going to mean your program is going to run pretty slowly, especially for inputs of size up to 100,000. To see if an algorithm that you've invented is slow, you can actually do a rough estimate. So the rule of thumb that I like to use is 20 million. And what do I mean by that? Well, we want to roughly estimate the number of times our program processes array elements or variables. So for example, if I did a for loop that goes from 1 to n, then this processes this variable I n times. So let's say n is 1,000,000. If n is 1,000,000, it's fine because it is less than 20 million, so it will probably run in time. And conversely, if this number is significantly bigger than 20 million, for example, this 5 billion number we have here, then it's probably not going to run in time. So armed with this new knowledge, let's come up with some algorithms that let us solve more test cases on this problem. So after playing around with some handmade cases on your own, you might notice something about the pairs. And that is that if we're choosing the position for our left endpoint, then we really only care about the leftmost occurrence of each value. So what do I mean by that? Well, you see how we have 2 1s in this sequence, a blue one and a red one? If we can go to the next slide. So as you can see, the blue one can pair up with the 4, and it can also pair up with the 5. But the red one not only can pair up with the 4 and the 5, but can also pair up with the 2 and the 3. So in particular, the blue one, the pairs that the blue one can make is a strict subset, well, not a strict subset, is a subset of the pairs that the red one can make. So this means that basically, if we are going to count the number of pairs, then we can just ignore all of the indices where the value isn't the first occurrence. So I guess if you want to go back to a time in which you received flyers or magazines in primary school, how they only give it to the eldest in your family, this is kind of the same thing, because schools want to get out their flyers to all of the families, but they don't want to spend too many flyers. So instead, they just give it out to the eldest. This is kind of a similar idea. So if we only pick the leftmost occurrence of each value as our I, if there are like only 10 distinct values in the sequence, then you only really have to check 10 indices, 10 possible candidates for our value of I. So if k is the number of distinct values in our sequence, we only actually have to check up to k times n pairs, which is really nice because for 50% of test cases in that problem, k was less than or equal to 10. And if we want to run our rule of thumb again, 10 times 100,000 is equal to 1 million, which is less than 20 million. So this will actually run in time and get us 50% of the test cases for that problem. Next slide, please. So 50% of the test cases is all good, but we're trying to aim for 100% of the test cases here. And here is our second observation. So the second observation is that the number of pairs that an index I can create is equal to the number of distinct elements after I. So by what I mean by index I can create, I mean that the number of pairs such that the value AI is going to be on the left-hand side of the pair. So remember, we're already only considering the leftmost occurrence of each value. So we've basically, let's suppose there were ones in here, we've basically removed all of the ones in the middle, and we're left with this single one on the left-hand side. So let's work through this example. Next slide, please. So here are the pairs that one can make. We can pair one up with 2. We can pair one up with 3. We can pair one up with 4. We can pair one up with 5. We can also pair one up with 6. So what we notice is that we can make 5 pairs. And indeed, there are 5 distinct elements after 1. There's 2, 3, 4, 5, 6. So upon playing with this example, you'll see that our observation actually makes quite a bit of sense. Because, of course, the number of pairs that an element can make is going to be equal to the distinct number of elements after them, since you don't want to double count. So what we want to do is we want to pre-calculate the number of distinct elements after each index. What do I mean by that? Well, let me just work through this sequence we have here as an example. So let's work from the end. After this index, we only have 1 distinct element. After this index, we have 2 distinct elements. We have 4 and 6. And then we have 3 distinct elements. We still have 3 distinct elements because we've seen 4 before. We have 4 distinct elements because we haven't seen 2. We've seen 2, so we still have 4. We haven't seen 3, so there's 5 now. And there's 5, and there's 6. So once we have pre-calculated this, let's store this in an array called U. And I'll be using this array U in the pseudocode on the next page. So like last time, we only want to consider the first occurrence of each value. This allows us to completely avoid double counting because we only consider each possible value for the left point exactly once. And also this allows us to check each left candidate index very quickly because all we have to do is we have to look up the value of this U array of the element next to it or the element to the right of it. So for example, if we were checking 1, all we'd have to do is access this array U and find that, okay, the value is 5. So 1 can make exactly 5 pairs. So this is really good because if all n elements are distinct, then basically we would have, with our previous algorithm, we would have been back at the start, right? We would have to test every single possible pair. But with this, since we only do a single calculation for each possible left candidate index, it means that we can speed up our algorithm a lot, especially on those really tough cases. So let's go to the next page. All right. So I've written down some pseudocode for this algorithm, and it's basically going to be everything we've discussed so far. So this U array is going to be the helper for distinct elements. This scene array is going to be help us determine if we've seen a value before. And of course, our answer stores our answer. So first of all, we want to pre-calculate the array U. And so we have, for the variable j, from index n-1 all the way down to index 0, we check, first of all, if j is greater than n-1, or basically if j is not the last element, then we want to inherit the number of distinct elements from the array element after us, because let's say there were 4 distinct elements after us, then obviously there'd be at least 4. Then obviously we would also have at least 4 distinct elements. And then we check if the element that we're currently looking at has been seen before. So if it has not been seen before, then we mark it as seen, right? So this means that we will basically keep track of, now that we've seen this element, we won't record that is the distinct element. And then because we hadn't seen this element before, we add 1 to our U array, or the distinct elements array. So this 4 becomes a 5. And we do this across the entire array going backwards. So for example, if I was back in my sample input of 1, 1, 2, 3, 2, first of all, this element would start at 0. We would see that we haven't seen it before, so this would be a 1 instead. Then we'd copy the 1 over. We see that we haven't seen this 3 before, so we get rid of it. We see that we have seen this 2 before, so we just copy the 2 over. We see that we haven't seen the 1 before, so that we add 1 to that. And we see that we have seen the 1 before, so we put the 3 here. And this is going to be our helper U array for the sample input. All right. So once we have done with the pre-calculation, we're going to reset this array scene because we're going to need to use it later. And we want to do this again. So this is going to be the forward sweep. This is where we'll be considering the leftmost occurrence of each value. So candidate left endpoints are going to be from index 0 to index n-2, because the last element of an array can't be a left endpoint because there's nothing for it to pair up with. So first of all, we check if this is the leftmost occurrence. And how do we do that? Well, if it is the leftmost occurrence of a value, then we definitely have not seen that value before. So we can just check if the scene array for our value is false, then we can simply set it to be so. And then we set, and then since we have now seen the value, we want to set it to true. And because we are considering this as a left index, like before, we take the value of the distinct elements array after us, and we want to add it to the answer because that is how many pairs this leftmost occurrence can make us. And then after this, we're done. In the answer will be the total number of distinct ordered pairs of elements that we can make. which is really good. So yeah, okay. So does anyone have any questions about this algorithm? I will show Python code for this on the next slide, but I'll wait a bit for everyone to post their questions. Oh yeah, another thing I want to mention is that since we're processing through this array, this for loop runs n times. And as you can see inside, we access a constant number of operations. And also here, this array or this loop goes n times, or n minus 1 times. And it also accesses a constant number of elements. So let's suppose that this does, I don't know, 10 accesses, and this does 10 as well. This is like a very high estimate, obviously. But with this estimate, we can determine that the number of accesses we'll use is 10 times n plus 10 times n minus 10, which is roughly 2 million, which is less than 20 million. So we're all good. This algorithm will run in time. All right, I don't see any questions in the chat. So I think we can go on to the next slide where we'll show some Python code. So this is a solution I implemented in Python and checked to make sure it's correct. And it's basically the pseudocode that I went through, but implemented in Python. So I guess a few things that we want that I want to mention is that since Python is zero indexed, be careful with optfire1 errors, especially because the values are between 1 to k. We want to actually initialize our scene array to k plus 1 elements. Here and here. Because if we query index k of scene, we want to make sure that there's actually a space for us. But apart from that implementation detail, this Python code is pretty straightforward and should solve the problem. All right, any final questions before we go on to the next problem? How does this deal with pairs like x comma x? All right, so the answer is that it just does it. For example, if the entire array was just ones, let's suppose, to put in very extreme case, we would build our distinct elements array, and once again, it would be all ones. And then we look at the leftmost occurrence of each value. There's only one value, and the leftmost occurrence is here. So we see that, okay, the number of distinct elements to the right of 1 is 1. So this one can make exactly one pair with the other ones, which is exactly 1, 1. So the answer is going to be 1. That is the most number of ones I've ever used in a single explanation. But yeah, keeping track of the number of distinct elements being invariant of the value of the left position means that we can just deal with these pairs quite elegantly. Yeah, so let's suppose, oh, do you mean 1 index 1 to 2 or 0 index 1 to 2? Oh, right. The list 1, 2 Oh, you mean like in the original problem? No, the list 1, 2 only has one pair, which is 1, 2. So yeah, you can't duplicate an element or whatever. It has to be like an index and then an index after that index to make a pair. And like, because the pairs are ordered, we also can't make the pair 2, 1, because 2 doesn't appear before 1 in this list. Does that answer your question? Oh, okay. So if you got runtime error, does that mean your code exceeded the time limit? I believe on HackerRank, runtime error means that your program crashed. I haven't looked too deep into it, but most of the time, if it says runtime error, that means your program compiled successfully, but it crashed on an input. All right, excellent. I think those are all of the problems. Those are all of the questions with pairs. In that case, we can go on to the next problem, which is going to be Banner 2 which is going to be presented by Angus, I think.
Yes, I'll present that now. So the next problem is Banner 2. I'll also briefly discuss Banner 1, although that's a lot easier of a problem. So in Banner, you're given in both banners, you're given a string consisting of the letters I, M, and C in some order. I'll give an example in a second. You can erase some of the letters, and there's 2 questions in Banner 2. First one is, what is the maximum number of consecutive strings of IMC? So like IMC, IMC, IMC would be 3 of them. They can be formed. And how many ways you can achieve this? 2 ways are considered different if a letter at a certain point is erased in one way and isn't erased in another. And I'll give some examples. So next slide. So here's a sample input. 8 is the number of characters. And then you see we have a string. So that's like a word consisting of the letters I, M, and C. And so if we go to the next slide, we see that if we erase those 2 characters here, so we get rid of these ones, then our final string is IMC, IMC. So we get 2 IMCs in a row. And then if we go to the next slide again, if instead we were to erase these 2, we would also get IMC, IMC, but it's a different way of doing it because we're erasing different characters. And finally, next slide again. If we get rid of these 2 characters, we get IMC, IMC as well. All 3 of these lead to 2 IMCs in your final thing. And there's 3 ways of doing it. So you output 2, that's the maximum number of IMCs you can make. There's no way to make 3, I think that's fairly clear. But there's 3 ways of doing it, the 3 ways I went through. And so in this problem, you can be given much larger inputs, up to I think 100,000. Remember the bounds correctly in the full problem. So you need an efficient algorithm to solve this. So I guess first of all, are there any questions about what the problem was asking? Give you 10 seconds or so for that. All right, let's move on then. So yeah, if we want to find the maximum number of IMCs, that's the first thing the question's asking. We can use a greedy algorithm. So next slide. The greedy algorithm is just take the first I, the first I, then the N that's after it, then the first C that's after it, etc. So in this example, we first take the first I, Then we can take the M after that, the C after that. Then we take the next I again, the next M, the next C, which is at the end there. And this greedy algorithm will lead to the maximum number of IMCs. A kind of quick proof, informal proof, I guess justification as to why it creates a maximum is that it's fairly obvious, I think, that you want to take the first available I in your ones that you're keeping, i.e. not deleting. Because there's no point your first I being this one here when choosing an I earlier on will give you more options later. By the same argument, we'll take the next available M, the next available C, etc. And we keep going like that. And then we count the number of complete IMCs we form, in this case 2. And that's our answer to the first part of the question. For banner 1, that was in the easier division. This was the entire problem, and this was the entire solution. But counting number of ways to do it, that's the hard part. So next slide. Yeah, the hard part is counting the number of ways to actually do this. So if we go, we're going to use a technique called dynamic programming. I'll describe the solution today, but we'll introduce dynamic programming more generally in a future workshop. So hopefully it's understandable today. If this is your first time seeing it, it's probably quite a complicated topic. So make sure to ask questions if you're confused. But yeah, we'll introduce this topic more generally and how it can be used to solve other problems in a future workshop. Today, I'll discuss how we can use dynamic programming just to solve this problem here. So a very basic rundown of DP is that we split a big problem into subproblems. So we're going to use 2 subproblems in this one. So the first one being, we're going to define a function FIC to be the maximum number of IMCs. Now, this is just for the first part of the problem. We're not counting the number of ways yet. We'll get to that later. But it's first of all a DP solution to solve the first part of the problem. So define the function FIC to be the maximum number of IMCs we can make if we start with the ith character, so 0 indexed in the input. And for the first IMC, we start at the letter C. So I think some examples will help that. If you go, we have the same input again. So in this case, what does F0I mean? So 0 index, so F0 means starting at the first character, and the first IMC should start with an I. And the answer is 2 because we can make a maximum of 2 IMCs. F1M. So F1M means we start at index 1, that's here. Now, what's the maximum number of IMCs we can make starting here? Well, it's just 1, like IMC. However, we have the condition that it's the first IMC starts with this second letter here. So if the first IMC starts with M, we can just go MC for the first IMC, and then IMC for the second one. So by this second condition, by this character C, I kind of mean for the first IMC, we can kind of ignore the start maybe, or ignore the first 2. So we can build it up one letter at a time. So starting at 1, the first one starts with M, we have MC, IMC for 2. We have a few more examples. So for the next one, 4, so 1, 2, 3, 4. Again, if we consider from here onwards, what's the most number of IMCs we can make starting with an I? That's just 1. That's these 3, IMC. 5I, again, if we start at 5 here, we can make 1 IMC starting with I. However, if we start at 6 here, we can make no IMC starting with I, because there's no I to start off with. So we can't make any, so the DP value will be 0. But if we can start our first IMC with an M, then we can just go MC. So this is this kind of function making, our dynamic programming state is often referred to as. And it's a smaller problem that might be a bit easier to solve. And so in fact, how can we do this? We go to the next slide. We're going to consider a few cases. So considering just Fi letter I, so this is some index in the string, and just considering IMC to start with an I, a few cases. Now what happens if I equals n? So I equals n in this case is actually 1 past the end, because the string is 0 index, so it goes from 0 to n take 1. So if we're 1 past the end, then obviously we can make 0 IMCs. Because there's no string left, we can't make any IMCs. So that case is trivial. This next case is a bit more complicated, but if you wrap your head around it, not too hard. So what's SI here? So SI is the ith character in the string. That's what I'm going to say it is. So if we have like IMC, MC, then S2 would be C. Remember, 0 indexed. So we're saying if the ith character is not an I, then the result of calling F on I is just the result on calling it on the next character. Why is that? Because this character is not an I, which means that the first IMC cannot start at my character, which means if we increase I by 1 and consider the first IMC starting from the next character, we're going to lead to the same number of IMCs because we're not an I, so we didn't start one off. And finally, the last case is if the current character is an I. If the current character is an I, then we greedily, as we discussed before, it makes sense to start our IMC at this I. It's the same reason for a greedy algorithm. Might as well start as early as possible. In that case, the DP value here, well, for the rest of the string, we're going to create as many IMCs as we can, but we already have the I, so we can create IMCs starting with an M. This is precisely why I have this second value in the state, because for like this I here, the number of ways to make IMC starting with an I here is the number of IMC starting from an M here, which is just one MC. And so that's where this comes from. Let me know if that doesn't make sense. There are two more cases. They're pretty much the same. So if we go next slide, F for IM, this is exactly the same as the previous one, just changing letters around. So not really worth explaining it because it's the exact same principle. This one's a bit more complicated. The only difference is this here. Why do we add 1? Well, in this state, we're considering the number of IMCs, which start, the first one starts with a C. So like C IMC, for example, would count as 2. Now, if the first character is a C, then we go, okay, the next one, but starting with an I. I'll get to the question in a second. But at this point, we've started a new IMC. So we should add 1 because this C is the end of an IMC. So we get 1 point for that one, plus any future IMCs we make. So the question was the number of IMCs made by erasing or not IMCs starting with this character. I'm not sure exact. Oh, so we're not erasing this character. Yeah, so to clarify, sorry. We've switched from, I should have made this distinction more clear. We're switching from erasing characters to selecting characters because that's probably a more natural way of putting it. So because they're equivalent, if we can delete some characters, equivalently we can select some characters. So in this case, what's the maximum number of IMCs considering all characters here onwards? We're not necessarily including I. We're just saying restrict this. I'll look at your example. If it has, so you're given IMC MC, F0I is 1. It's 1 because IMC. So yeah, we're creating IMCs by deleting characters, the same as what the problem asks. So in particular, F0I will be the answer to the problem. The max number of IMCs you can create by deleting characters. So yeah, in this case, we'll delete these two, leading to this. But deleting characters is equivalent to selecting every character we don't delete, which is why I've spoken that way. Does that make sense? Isn't F1M equal to 2? Let's go through that. So we have our input, IMC, MC, and let's go through this. So we're looking at F1M. What's F1M equal to? F1M, that's this case, not this case there, it's this case, F1M, that's this case here, because character 1 is an M, and that's equal to Fi plus 1C. So we're saying this is equal to F of 2C. What's f of 2c equal to? That's equal to f of, that's this case here again, because the second character is a c, so that's equal to f of 3i plus 1. What's f of 3i? Well, f of 3i, that's this case here, is equal to f of 4i. What's f of 4i? That case again is equal to f of 5i. What's f of 5i? Should be f of 5i. That's equal to 0. That's this case here. So overall, we get 1 as our answer. We get 0 plus 1 equals 1. So do you understand that f of 1m is equal to 1 based on what I just went through? And so from that, f of 0i is equal to f of 1m, which is equal to 1 I just went through. Exactly. So as Alex said, you only ever add 1 when you move from a C to an I. And the reason why you only add 1 when you go from a C to an I is that corresponds to completing an IMC. We've finished an IMC, we're starting the next one, which is why we add 1 here. We don't add 1 for any of these cases. And so this is, yeah, it is confusing. But once you understand this just gives I'm going to use the word simple, maybe not conceptually simple, but certainly pretty simple to describe and code up function for computing the answer, like this. However, we already had a greedy algorithm to do this. So why does this help us? Well, it will help us count the number of combinations. So if we go to the next slide, we're going to define g of ix very similar. Replace x with a c maybe. Sorry, that's typo. G of IC will be defined in a similar way, except it's a number of ways to achieve the maximum. So that is the second part of the question. So how do we go through this? Well, again, we'll give a recursive definition. If I equals n, we go with 1. Why is that? Well, if we're at the end of the string, we can create 0 IMCs. How many ways to do that? Well, there's only one way, and that way is to do nothing. Reach the end of the string, which is why there's a 1 there. Case 2, the same as the previous case 2. If the current character is not an I, well, in that case, it's just the number of ways of, so we've got a string like IMC, IM, let's say. Let's say we're character 1, that is SI is not I. Well, the number of ways to create an IMC starting from here is just number of ways to create an IMC starting from here, because we don't start any IMCs here. So by the same arguments before, the number of combinations is the same as this one. The next case is where it gets a bit different. So we have 2 conditions here. The first condition is if SI equals I, that is the last case, but it was split into 2 subcases. So from before, a greedy algorithm, I'll just draw the input IMC, MC. A greedy algorithm says, well, we want to take this I, and then this M, and then this C. However, we can also take this I, and then this M, and then this C, and they'll both lead to 1 IMC. In fact, there's a few ways of doing it. We can also go this I, then this M, then this C, etc. But notably, actually, this is the wrong example for this instance. My bad. A different example is if we have I, MC. So our greedy algorithm says we should always take the first I. However, in this case, we can take the second I, and that might work. However, this condition here guarantees that we must take the first I. Why does it say we must take the first I? Because this condition says, well, this is what happens if we take the I, we go to the next character, and we start looking for an M. And this here says we don't take the I, we go to the next character looking for an I. And this condition, this greater than sign, says, well, if we take the I and start looking for an M, that leads to a better solution than if we take the I, we don't take the I, and so look for an I again. So in that case, if this inequality holds here, then the optimal answer has to be formed by taking the first I. So we just take this. That is the number of combinations if we take the first I. The final case is what's left. The last case is, well, what if these two things are the same? This can never be greater than that. I won't go into it too much. That's just because of the greedy algorithm. So the last case is if they're equal. In that case, we add these two cases together because we go, well, in this case, it's equally optimal to take this I or to not take this I and go looking for an I in the future and take this I. And so we should add the number of combinations of both moves together, which is exactly what this does here. So yeah, note in the last case, both lead to an optimal solution. The cases for M and C are quite similar. So if this is an M or a C, just you have to factor in the +1 for the C case, but they're quite similar, so I've omitted them. Does this function make sense? Again, it is perhaps quite a confusing formulation. But there aren't any comments about it. Does Odin buy that it works? I'll get to that in a second. So let's go to the next slide. So first of all, what is the answer? The answer to the overall question is just f of 0i and g of 0i. That is the maximum number of IMCs and number of ways to do it. And so the question was, why is the recursive solution faster? Well, we already had a greedy solution for this first problem that was quite fast. However, we didn't even have a solution to count number of ways. So this is the first solution I presented, the first non-trivial solution that counts number of combinations. And let's look at how fast it is. So time complexity, this is a formal way of working out how fast a program is. But basically what this means is there's order n states. In particular, there's like 3 n states where a state is a possible function call. Or in fact, there's actually 6 n states because remember there's f and g. So between f and g, there's 6 n states. What are these? These states are like f of I, g of I, then like f of I m, g of I m, f of IC, g of IC for each I. So there's 6 n states, that is possible function calls we can make that will result in distinct answers. In each state, we do constant work. By constant work, I mean we call a number of other functions. Now, this is kind of implementation detail, but if you implement these functions naively, then like f of 0i will like call some functions that'll call some more functions, and you might have some tree branching. However, again, we'll get to this more in the DP workshop, but if you cache the answers to the function calls, that is, you only ever compute the answer to a given function call once, because every time you call f of 0i, you'll get the same answer. If you cache function calls, then you only compute each function call once. So you're computing 6n different functions. Each one takes constant time because you're looking up a bunch of other values. So it's linear time overall, which for those of you who know time complexity means it's the same time complexity as the greedy algorithm. For people who don't know time complexity, this just means it runs in approximately proportional to the size of the input. So for 100,000, for 100,000 string size, there's 600,000 states. So it's doing about 600,000 things. Tunan in the previous one mentioned, I think, approximate rough way of estimating time, and 600,000 operations you can definitely do in 1 second. this algorithm will be fast enough. This is mathematically perhaps more complicated than some of the other problems so far, but hopefully that made sense. Do people understand why this works and why it's fairly fast? And why it computes both answers? Yep. Again, if you haven't seen DP before, this might be a bit confusing, but this is kind of a common technique. We do a similar thing to this. And so once you know how it works, it becomes a lot easier to understand. So I haven't given the code for this. The main reason being the code, if you just go back to like the previous slide, or like go back to the one before this, like the code for F is literally just like, these is all a bunch of if statements. If you're smart, you can do a few less if statements, but like at worst, you have like 9 different if statements for 9 cases. This is what your code looks like basically. And then you implement G again by considering all the cases. So the code is not pretty simple once you understand all the cases. It does, yes. So one detail is you need to store the fn values in an array because you need to cache your answers. That's the one non-trivial detail, is you need to store the answers in an array. Another detail, there are a few ways to implement it. You don't have to implement these functions recursively. You can do it using a for loop by noting that like g of I will always call g of I plus 1. So if you iterate backwards, you can compute it starting from like g of n for all characters, then use them to compute g of n minus 1, etc. So you can go backwards and just store an array and use a for loop, or you can do it recursively and just cache any results in a array. Does that hand-wavily make sense? Again, this will make more sense once you know how DP works. Give another 30 seconds for any questions. If not, we'll move on to the next question. Yeah, so DP, yes. So DP is an optimized version of recursion. So if you implemented this without cache, it's called memoization. Can I spell it right? I think that might be a Z instead of an S, memoization. This is the term used about caching results. And yeah, without memoization, it would be like this function here would be at worst case like order the 2 to the n or something. You could probably prove a better bound, but either way, it would be exponential because of like these 2 function calls here. But once you cache the results, it becomes linear. Okay. This is probably theoretically the hardest problem, I would say, in the contest. I wouldn't say it, like, it wasn't the last question. It's not the hardest problem if you know DP. But if you don't know DP, my opinion, this is probably the hardest problem in the contest. Because it uses this technique. It is covered in some uni courses. I don't know exactly which ones. Does 2521 might cover DP? I can't remember. If not, like the algorithms course, 3121 covers it. 3121 covers it. Also 4128 in more detail, which is a competitive programming course. So yeah, I think 3121 is compulsory, right? So at some point in your degree, you will learn DP. Yep. Okay. So if there's no more questions, we'll move on to the next problem.
All right. Thank you, Angus. So the next problem will be presented by Isaiah, and it's going to be restrictions.
Yep. Okay. So in this problem, it's kind of interesting in that you're constructing something. So you're not just printing a number at the end. You're printing like a street, and in particular, you're asked to print a street which has as many houses as possible, subject to R restrictions, each stating that there can't be any more than Y houses in any X consecutive spaces. So pretty much the houses can't be really dense. So that's an example input. That's how long your house is going to be, that 8. The 2 is the number of lines following, so it doesn't really matter. And the first one, I crossed it out. That's not what I meant to do. The first one says, in any 3 consecutive spaces, in any 6 consecutive spaces, you can't build more than 3. So you can build any 3 houses, but you can't build more than 3 in any 6 consecutive spots. And similarly for that one, in any 3 consecutive spots, you can't build more than 2. And so as your output, it's not a number, as I said, it's a string in this case, and we chose to represent it as a H for a house and an underscore for no house. And this is a house that obeys all the restrictions. You can check that in any consecutive 6 spaces, there'll be no more than 3 houses, and in any consecutive 3 spaces, there'll be no more than 2 houses. Yeah. And also, importantly, this is the most houses you can fit. Like obviously, if you have like just 8 empty spots, then that will be a valid street, but it doesn't have the maximum number of houses. You can obviously see you can add 1 more, or in fact 5 more, and that's the sample output. And there's like, you can also see that there's other possible outputs. Like you could flip that whole array, you could possibly shuffle some houses around and it'd still be a valid output, which is maybe a bit different to some problems that you've seen. Okay, constraints are probably smaller than almost all the problems that we've seen today. Instead of the usual 10 to the 5, which is a very common number, we have 10 to the 4. And this one's very small, it's only 100. And that kind of hints towards what kind of solution we can have. So since R is small, we could have like a big factor of R, but in fact, I guess we'll come to the solution and we'll see what the complexity is. But even though the size of the input is only R numbers, it's probably impossible to solve it in order of R operations. We'll see that soon. And there's a subtask as well, which is small n. Okay. I guess I'll give 10 seconds if anyone doesn't understand the problem. Analysis. Oh gosh, did I cook the sample output again? That is so bad. Okay, I stuffed it up in the contest. I apparently stuffed it up here as well. What did Tunan say?
Yep. So the actual sample output is house, no house, house, no house, house, no house, house, house.
Why do I suck? Okay, that is an actual valid sample output. Nice. I must have copied the original one or something. Okay. Cool. Okay, I think we're happy with the problem. So we'll go on to the solution. I found this really hard to motivate the solution, but I guess if you play around on paper a bit with a few cases, with the sample case, some other small cases, you'll come up with a possible method for constructing an optimal solution. And that is to go from left to right and always place the house unless it violates a restriction. And violates a restriction pretty much just means you put too many houses in a small place, in a small number of spaces. And I'll go back to X's and Y's later, but that's the basic idea. And I think it's too useful to define it. So this is a greedy algorithm. We're going from left to right and always placing a house unless it violates a restriction. And we've seen a couple of greedy algorithms today. I'll go into a bit more detail about how exactly how we can prove that this greedy works, because it's good to like see at least one proof of how greedies work. And this one's not too hard. So it's kind of a proof by contradiction, not really though. So we suppose that we have gone from left to right, placing houses. I'll draw up the sample input again. So say we have done some stuff here. Say we've put, actually just ignore these restrictions. Just pretend this is a hypothetical case. We've put some houses there and we're now up to this one. And we're deciding whether to build a house here. And suppose we don't build a house here, even though putting it here won't break any restrictions. I think the sample input is fine, but I'm really bad at sample inputs apparently. But I think in this case, you could put a house here and it wouldn't break any restrictions. So suppose we don't put a house there. And so eventually we're going to have some houses later on. If there's no houses later on, that's kind of a trivial case. We might as well have put it there and we would have got a higher score. So let's say we put some houses here, down here. Okay, now we use an argument, I guess it's somewhat of an exchange argument to show that we could have done no worse if we put a house earlier. So there's probably a few ways to formulate this, but the way that I came up with is you consider the next house. So remember we're considering this spot. We didn't put a house there even though we could. We consider this house and we think, why didn't we just move this over along to here and put it here instead? And so we need to firstly show that, so in order for this proof to finish, just so we know where we're going, we want to show that this is the thing that we can do. Firstly, this is the thing that we can do, and secondly, that this won't lead to any worse outcome in the end. So less houses at the end of the day. I've done a great job of writing over where my words will be. So, but I'll just do it. So it's fairly clear that if there were any restrictions, so I guess here I'm considering the restrictions as belonging to each house. So each house has to obey the restriction in that it can't have too many houses close to it. You could make this much more formal, but I think especially for a proof of for a contest like this, it's good to just get it intuitively, and it's somewhat rigorous, but it could be more mathematical, I guess. So consider any house to the right of the one that we moved. By moving this house back, we're moving it further away from any of these houses. So we're not going to like make it more dense on that side, on that right side. So we're not going to break any restrictions on that side. And we're also not going to break any houses on the left because of our supposition, which was that we could have placed the house here. So if we could have placed the house here, then it didn't like conflict with any of this stuff here. So by moving the thing here, we have not changed any conflicts here. We've not changed any conflicts here. And therefore, it's a valid move to make. I'll clear that now. I'll clear that. Okay. So we've shown that this is a valid move. Maybe I shouldn't have cleared it, but it's gone now. So we've shown that that was valid. So now we need to show that we couldn't have done any better. Rather that doing this is like not any worse. So okay, I brought it back. So if you think about what we did when we moved that house, you kind of like, you don't actually need to say this to conclude the proof, but you can kind of imagine if we repeat this process, and we could have shuffled a bunch of houses over. Maybe we couldn't have shuffled any more houses over. Maybe our thing was already like as full as it could have been, but in some cases we'll be able to shuffle houses over. So in some cases we'll be able to do better. by placing the house where we didn't, but we could have. But in no cases will we be worse off because we haven't changed anything later on. So we haven't ruined any future decisions. We haven't affected any future decisions for the worse. We've only affected them for the better. Yeah, okay. That's it for the proof. It's probably a bit different to what you've seen in any workshop or today. I think it's conceptually quite simple, but getting the details straight in your head and understanding it in words is a bit harder. So I'll give half a minute for people to ask any questions about that. Okay, it seems like people are happy with why the greedy is optimal. So I'll move on to implementing this. So if you look at the steps, the steps are at the top. We just move from left to right. We have our end spaces. Move from left to right, and we place a house unless it violates a restriction. And that pretty much is a solution. You just have to flesh it out in code. So I guess I'll work through the input, if I remember right. Okay. So we can build a house in this first spot. I think you can actually always build a house in the first spot because the constraints aren't that silly. So we can build a house there. And now we actually have to think, if we build a house here, are we going to break this restriction? This restriction says we can't build more than 3 in any range of 6, which is fine. We're not going to build more than 3 in a range of 6, and we're not going to build more than 2 in a range of 3 either. So we can build that. Now the next one, we look at 6. If we build one here, we're not going to build more than 3 in a range of 6. We're going to build 3 in a range of 6, but we're not going to build more than 3 in a range of 6. But so this restriction is fine on this at this particular space. However, this one is not fine because we can't have more than 2 in 3 consecutive blocks. So we can't have 3 there. That's not allowed. So this one is nothing. And so that one is quite clearly, you can put one there. And then this one, it won't violate this one, but it will violate this one. So we can't build it there because I guess a somewhat subtle point is that we haven't even reached 6 ranges yet. But if we build it here, then we've built more than 3 houses in 5. And that means we're going to eventually have built more than 3 houses in 6 as well. So kind of have to plan ahead and make sure we don't violate any restrictions in the future either, even though we haven't really violated it yet. Or you could see it as we've already violated it because at some point it's going to break. And I think the input, this is not like a troll contest. So this will always be less than n. So it will always break eventually if you do that kind of thing. Okay. And if we continue in this manner, then we can build one there. And so then there's these 6 that we have to consider to potentially break it. And there's 3 there already, so we can't build another one. There's a house there. Okay, and that's the exact reverse of turn on sample. So I've somehow managed to get this one right. So turn on sample, which is just the reverse of this, which was, you can read it in chat. It's just from right to left, is also going to work. And as I said, you can print either of them, and you'll get a correct verdict. Okay. So I've just pretty much worked through what that all says. So we're looping over n things, n spaces. For each of them, we check over all our restrictions, and we check if there's greater than or equal to y houses in less than or equal to x spaces. I think that should be greater than y houses. very nicely corrected there. We shouldn't build more than y houses in less than equal to x y spaces. And that less than equal to is fairly important. That is important because of that case that we covered earlier, where we broke the restriction before we'd even seen x sub I many spaces yet. Okay. So that's how we check each restriction. We just check that, and we'll get into the implementation in a little bit, and we'll see how that's implemented. Check each restriction. Yeah. So for time complexity, there's n spaces. That's a factor of n. There's r restrictions, and each restriction you check the previous xi spaces, and xi can be up to n, as I said, so it's order n. So that's n times r times n, which is n squared r. And if we remember the bounds, they were n equals 100k, r equals 100, and the subtask was n equals 100. And so if you do the numbers, n squared r will be 1 million, which is fine for the subtask, for the first subtask, or the only subtask, and n squared r for 100k times 100 will be 10 billion or so, which is definitely not going to pass unless the data is really weak, which I hope it wasn't. Okay, so we need to optimize this. I think in the contest it was worth about 60 points, 70 points without this optimization. But the optimization is prefix sum, which is something that was covered in the first workshop. And for those people who weren't there, very briefly, it is, so if we're checking a restriction, we're checking how many houses were built in this range. If we're checking, if we're trying to build a house here, so we have a candidate house there. We have some houses here. Let's add some more. So it's more stuff. So we're checking that range. We want to check how many houses are in here. Now, if you remember, if people were following the prefix sum lecture, or workshop rather, the main trick was computing sums over ranges quickly. And how do we do that? We take the size of this range and we subtract the sum of this range. We take the sum of this range and subtract the sum of this range. In this case, it's not really sums, it's just counts of how many houses there are, because there's either one or zero houses in each space. So we keep track at any point of how many houses are to the left of it, and then we can use this subtraction method of prefix sums to see how many houses there were, and hence we can check if we've broken the restriction very quickly. We just check if our prefix sum is greater than y, supposing we have the house there. Cool. So in that case, this step changed from O(n) to O(1). So we got rid of a factor of n, so it's order nr, which is the intended solution for the problem. And it passes because 10k times 100 is 1 million, which ended up being the same number as this, kind of nicely. Cool. Okay. Yeah. So this is kind of a footnote, so I'll just go through it. It's not super important. So if you have any questions about that, feel free to chuck them in the chat while I'm talking. Yeah, so I thought about this. Some other people thought about this for a while. This solution's order nr, and if you think about it, the input size is only r, right? So it feels like we should be able to do the problem faster. Something like order r or order n plus r or something like that. And so that's an unsolved exercise for the viewer is to solve the problem in a faster time complexity. And it's also possible that you can't actually do that, or it's very, or there's no known algorithm currently that will ever be able to solve that. And in that case, you can enjoy trying to get the details of why we can't currently solve that. And I guess I'll tell you, so it's not too impossible, is there's a famous problem in computer science called the Knapsack Problem. And it's possible that you can show that the Knapsack Problem can be solved fast if you can solve the restrictions problem fast. That's my conjecture. I don't know if it's true. It's a good chance it's not. It'd be kind of cool if it's true. And so if you can solve Knapsack fast, you can solve restrictions fast. Rather, if you can solve restrictions fast, you can solve Knapsack fast. And Knapsack doesn't have a very fast solution known, doesn't have a fast solution. I think it's somewhat similar to NR, with some different variable names and whatever. But and so since Knapsack doesn't have a fast solution, if my conjecture is true, then you can't solve restrictions any faster than this either. Okay. Yeah, okay. I'll pause for a tiny bit. And then I'll go over this. Okay, so again, this is just pretty much a transcription of the algorithm described, but in Python code. So you can see that I've set up the prefix on here because we're doing the faster solution here. And you can see that we have that outer loop, which is N, and that inner loop, which is R. And so for each space, we're checking whether we can build. So we check against all the restrictions. I think we start off by assuming we're not going to build a house. So we just say that we append to our prefix sum, we're not building anything. So it's just going to be the number of houses before this is going to be the same as the number of houses before the previous one. And then, so for each restriction, we check, will it violate it? So is there currently a number of, so remember we haven't built it yet. So it's kind of different to what I said before. So if we don't build and there's already more than Y houses, then if we build one, then it will go over the restriction. So we can't build. So we set this flag, which is pretty much just alerting this later half of the loop that we don't want to build a house. So if we break a restriction, we tell this half of our program, don't build yet. You could also break this is very tiny, but you can break there. That doesn't really matter. The worst case, it won't change the worst case. So yeah, I guess the magic line in this piece of code is that line there. And this considers the last X elements. So if X was 5, it would consider those and make sure that there's not, if X is 5, Y is 3, it checks the last 5. If we're trying to build here, it checks the last 5. If there's more than 3 already, we can't build one here. And if there's less than 3 already, we can build one here and we won't violate that restriction. Okay. Yeah, and I think those comments are self-explanatory. We print a house if we can build it, and we don't if we don't, according to our greedy algorithm that we discussed. Okay. That is pretty much the end of the solution for this problem. Yeah, so I guess we'll just wait 30 seconds for questions. We can move on.
Sure.
Just one thing while people might be typing questions is, like in terms of the contest, I think like this problem is quite easy to implement, but perhaps if you haven't seen like many similar problems before, or it's kind of an ad hoc problem, but if you haven't seen many problems before, or many problems in the style of ad hoc or informatics problems, then this would be kind of hard to come up with. But the code is very short. And if you don't use prefix sum, actually, if you don't use prefix sum, it's probably a bit longer because you need to set up a for loop in here instead of the prefix sum, and have like a count for how many things you've had. But yeah, I think this problem is like more about the proof. The more interesting part is about the proof and like why the greedy works than the actual code and the implementation details. Okay, I think people are happy to move on.
All right. Okay, so thank you, Isaiah. And I will be presenting the final problem, which is going to be Mexican wave. So for Mexican wave, the problem is that you're given an array of n positive integers and also an integer k. And you're asked how many subarrays or ranges of this array have all of the elements 1 to k. For example, on this sample input, we have 7. We have, okay, first of all, let's count these ranges now. So the 7 ranges we have, let's suppose we start here. So we would have the range 3, 2, 1. Since k is equal to 2, we want to contain the elements 1 to 2. We also need 3, 2, 1, 4. And 3, 2, 1, 4, 2. With regards to your question, I don't think we'll be presenting trading at IMC2 during this workshop, but we'll be writing an editorial for it if there's enough interest, and I think there's enough interest. Okay, so as I was saying, let's start at the left element here. So if we were starting at 2, we would have the subarrays 2, 1, 2, 1, 4, and 2, 1, 4, 2. And then if we were to start at 1 here, we'd have the subarray 1, 4, 2. And these are the only 7 subarrays, or the only 7 ranges that contain the elements 1 and 2. So when you're solving this problem, again, it is strongly encouraged to play around with some test cases by hand, so you might observe some patterns. And in particular, I'm going to present some observations that I get from playing around with this problem and playing around with some of the test cases. All right, so let's begin. Next slide, please. Here's observation number 1. Let's suppose we have a range of elements from L to R that can form a valid Mexican wave. Then if we expand that range 1 to the left, so instead of EL to ER, we go EL minus 1 to ER. Or we expand it 1 to the right, so EL to ER plus 1. Then those ranges can also form a valid Mexican wave. So for example, we still have our k equals 2 here. When we contain the elements 1 and 2, this is our range. And we know that this range can form a valid Mexican wave because it contains the elements 1 and 2. Because we know that this range can form a valid Mexican wave, then we know that expanding it 1 to the left, so 4, 1, 2, is also a valid Mexican wave, and expanding it 1 to the right, 1, 2, 3, is also a valid Mexican wave. And in fact, you can expand it even more. So since we know that 1, 2, 3 is a valid Mexican wave, we know that 4, 1, 2, 3 is a valid Mexican wave. And 1, 2, 3, 5 is a valid Mexican wave. And 4, 1, 2, 3, 5 is a valid Mexican wave. So in this way, if we're able to identify a valid Mexican wave, we can actually imply that a lot of other ranges are also valid Mexican waves, which is a really important observation. And we're going to use this later when we try and formulate a solution. So next slide, please. Let's play around with some inputs. So suppose we fix our right endpoint. Let's say we fix it here. Suppose we fix our right endpoint for our subarray. What is the furthest left endpoint such that it is not a valid Mexican wave? So I've just drawn this example in bigger so I can draw slightly better. So this is going to be our right endpoint, and we can expand anywhere to the left. So first of all, the range 1, 2, 3, 1 is a valid Mexican wave if we consider k equals 3, because it contains all the elements 1, 2, and 3. And so you'll find that the furthest we can place this left endpoint such that it is not a valid Mexican wave is actually slightly after this 2. So where we would place it is we would place it at 3, 1. So for this right endpoint, the furthest left endpoint such that it is not a valid Mexican wave is going to be the element before it, or 3. As if you expand it, you include all the elements 1, 2, and 3, and that's bad. So what happens if we keep this in mind, but let's try and consider it for the next element. So for the element 2 here, the furthest left endpoint so that it is not a valid Mexican wave is 1. Because if we move it further to the left, we'll include this 3 here, and that's bad because that means we'll make a valid Mexican wave. Similarly, if we go to this next element and consider this is the right endpoint, we figure that our left endpoint actually hasn't changed. It is still going to be this 1. And it will never go to the left because going to the left means we'll include this 3 again, and that's bad because then we'll have all the elements from 1 to 3. Okay, so you might realize something from this, and that is that all of the elements, as you increase the right endpoint, the left endpoint also increases. So what I mean by that is, let's suppose for this range, the element is here. If we move it one to the right, then this element to the left will only ever move to the right. And you see it moves 1 position to the right here, and it moves 1 position to the right again if we move our right endpoint to the right, and it moves 1 position to the right again. So that is a good way of maintaining this furthest left endpoint such that it is not a valid Mexican wave, which is really nice because we can now leverage this to our advantage. Next slide, please. So we want to keep track of how many of each element in our range to check. Actually, no, I'll get to that soon. So for now, what will we do once we have this furthest left endpoint? So considering our right endpoint is here, we know that if we place our left endpoint anywhere beyond this left endpoint, we will get a valid Mexican wave, which is really great because we want to count the number of ranges such that it's a valid Mexican wave. So if we mark these by indices, we'll realize that if our left endpoint is at index 3, there are 3 valid Mexican waves that end at this right endpoint, because we can expand it 1 to the left, and that's valid. We can expand it 1 to the left again, and that's valid. We can expand it 1 to the left again. So if we can just iterate for each right endpoint and find the furthest left endpoint, we'll be able to figure out very quickly and very efficiently the number of left endpoints such that the right endpoint with the left endpoint forms a valid Mexican wave. So how do we keep track of this efficiently? How do we determine if our range is a valid Mexican wave efficiently? Well, one thing we can do is we can just keep track of all the elements from 1 to k, and we want to make sure that at least one of those elements doesn't exist. And a way we can do that is we can declare like a frequency array of like 1 to k, and then you just query, okay, does frequency k equal 0? Does frequency of I equal to 0 for any I from 1 to k? And if the frequency of I is equal to 0, then you know that it's not a valid Mexican wave because that element doesn't exist. Now, there's a very efficient way to keep track of this, and it is when you realize that every time you move your right endpoint to the right, or you move your left endpoint to the right, you are either adding or removing a single element, which means that only one position in the frequency array is ever edited. This means that what we can instead do, instead of checking all I from 1 to k every single step, is we can simply maintain the number of zeros, or the number of frequency 0 elements. In our array, or in our range. Which is excellent. So let's go to the next page where I'll have some, I think, pseudocode to explain how this is going to work. So first of all, we will have our frequency array, as you can see, of length k. Well, actually of length k plus 1, because we're going to include all the elements from 1 to k, and since our arrays are 0 indexed, we want to declare an array of length k plus 1 instead. And then we initialize our variables. First of all, since this frequency array has all zeros, we declare the number of zeros in our current frequency array to be k. We declare our answer to be 0, and we declare the left endpoint to be 0. And so what we're essentially going to do programmatically is we're going to go through this array, and we're going to advance the right endpoint one at a time. So the right endpoint is going to go here, then it's going to go here, then it's going to go here, then it's going to go here. And the right endpoint is essentially going to like pull the left endpoint over. So this technique is what's called a 2 pointers technique. And essentially, the left endpoint is only going to move when it is forced to. And when is it forced to? It is forced to when the right endpoint adds an element such that it becomes a valid Mexican wave. So the left endpoint has to move forward. So, armed with this, let's look at our code. So, first of all, this is the right endpoint advancing. So this is one of the pointers. Mark the 2 pointers technique there. And first of all, we want to check, is this an element that we care about? Because if it's greater than k, then we really don't care about it, because it's not going to contribute to our energy values and determine if it's going to be a valid Mexican wave. Which is, so let's suppose that it is less than or equal to k. Then we check, okay, so since we're advancing the right endpoint, we're going to add this element into our frequency array. So we check, was the position in this frequency array originally 0? If it is, then we update the number of zeros, because we are about to set this 0 to a 1. And then once we update the number of zeros, we increment the frequency of the element we just saw. And now the second step is the left pointer. So this is basically the idea of the left pointer getting pulled towards the right. So while num0s equals 0, what that means is while all of the elements from 1 to k exist in our range, so basically none of them have frequency 0, we want to advance our left endpoint. So first of all, we check. At our current left endpoint, if it is a value if it is a value that matters and we care about it, which means it's less than or equal to k, then we decrement the frequency of that element by 1. And then we check, is the frequency now 0? If the frequency is now 0, then it wasn't 0 before, right? So we want to add 1. We want to add 1 to the number of zeros since we're maintaining this the entire time. And in fact, we could actually just break out of the loop here because the number of zeros is equal to 1. But we need to do one final thing, and that is to increment the left pointer here because we wanted to move it to the right. And so once we move it to the right, we will know that after this loop runs, what happened there? After this loop runs, this left pointer and this right pointer are going to just barely not form a valid Mexican wave, which means that any elements before it are going to form a valid Mexican wave. And so the cool thing about array indices starting at 0 is that if you're at index L, that means that there are exactly L elements less than you, which means that if we want to add the number of ranges that end at our point R, it's just going to be this element L here. So this is going to be the number of elements that form valid Mexican waves with R. And once we finish this loop, we will have our answer stored in the answer variable, which we can output after we've run this loop. So since we only run over this loop, since there is only actually one real loop here, and it's the right pointer advancing, and the left pointer is kind of only being dragged by the right pointer, we know that both of these pointers will take at most n steps each. And within those n steps, we take like some constant number of operations here and some constant number of operations here. So let's suppose we had like 10 for each. Then once again, this would be 20 times n, which is going to be 2 million, which is less than 2 times 10 to the 7 or 20 million. So that means that this algorithm will run in time, which is great. One final detail though, is that if you're implementing this in C, or like I say, any language that doesn't have arbitrary precision integers, sometimes, since n is less than to 100,000, sometimes this answer will actually overflow the signed integer limit of 2 billion. And that is bad because if it overflows, then it's going to overflow into the negative numbers. Oh, oops. I didn't fix that name. Anyway, it's going to overflow into the negative numbers, and that's bad because you want to output a big number as your answer. So the solution to that is to use 64-bit integer data types. So I know in C and C++, they're going to be called long. So if anyone wants to implement this solution in C or C++, then you probably want to use the long data type for storing your answer variable. All right. So on the next page, we'll have some Python code. Feel free to ask a few questions if you have any about this algorithm, because this was the final problem of division A, and it's quite, I guess, it's quite a niche, not a niche technique. It's quite a hard to understand technique if you've only seen it for the first time. So yeah, the Python code here, you can see this is our frequency array. We initialize these as our answers, and this is our left pointer. And then we advance our right pointer one by one. And this is going to be our advancing step. And this is going to be the left pointer catching up. And it uses the same logic as I described in the pseudocode. And finally, we add left pointer to answer. And then after we run the loop, we just print out the answer, which should give the number of valid ranges. So yeah, that's how that Python works. So this problem, let's run over the problem again, I guess. So you have an array with a bunch of values in the array. Let's give an example, I guess. 1, 2, 5, 4, 3. And you're given a bunch of queries of the form IX. So you've been given a bunch of queries of the form IX, and it's going to be equal to find the maximum of element I plus X, element I plus 2X, and so on until the end of the array. So you want to answer these queries quickly. And for that, we're going to consider two different cases. So the first case we're going to consider is the case where X is incredibly large. So we know that our element N is up to 100,000. So let's say X is, I don't know, something like 10,000.
Tina, there's a question.
Oh, yeah, I've been not looking at chat. Oh no, I see chat. Yep, this is an n-square n solution. Let me chat here. Yeah, I think a few square root solutions do get TLE, especially in Python, because Python on HackerRank is incredible. No, Python generally is really slow, and like even if HackerRank tries to compensate for it, it's really bad. But yeah, I guess we can try comparing. Oh, C++, yeah, then I don't know. I don't know how much the model C++, I don't know how long, how much of time the model C++ solution took, but I don't think it was too much. Right. But I guess we could like compare the solution to see if yours is the same. So I guess if X equals 10K, then what you can do is, because the number of query points is so small, you can just query position I plus X, and so on, all the way up to the end. And this will take a small number of elements, which is good because we want a small number of queries. And on the other hand, if we have X is incredibly small, like X is equal to 2, then what we can do is we can just pre-calculate the answers for small x. So for example, we have a bunch of arrays, and let's suppose this one is for x equals 1. Then for each element, we store the answer for q of I1. And then we do another array where we store q of I2. And then q of I3. And then so on. So this is also incredibly quick because it's an auto end pre-calculation, and we're really only limited by the number of times we have to pre-calculate. And these solutions will meet in the middle because both of them are incredibly efficient for their applications. So where exactly they meet in the middle, we can actually test. So let's suppose that they meet in the middle at position K. So anything greater than K, you use the first solution for large X, and anything smaller than K, we use the solution for small x. So that means that our time complexity is going to be okay. So we use for each individual value of x, we use order n to calculate the array. So this would be kn. And then for anything larger, it depends on the number of queries, right? So here, as you can see, it takes roughly n over k for each query, and then you multiply by q, the number of queries. And since n and q are roughly similar in size, I think so. Actually, they might not be, but I'm not sure. I had to read the problem again. But since n and q, let's suppose they're roughly similar in size, then we can just assume that n equals q. So we have kn plus n over k times n, which is going to be k plus n over k times n. And I guess anytime you see this sort of thing, you want to minimize this so that your time complexity, or like the number of operations you take, is the smallest. And for that, you want to select k to be equal to square root of n. And so that is how the square root algorithm is motivated. Was that roughly what you had? Yeah. Okay. So I guess I'll go over a few ways that you can optimize a square root solution, because apparently it was a squeeze. So the first one is you want to just fix the value of k as a constant. So this means that no matter what value of n you have, the value of k is always going to be some constant depending on the largest value of n you have. And so here, what we have is basically, even if n is like 10, we still take k to be something like 300. Because it doesn't really hurt to do so. The time complexity doesn't really get hurt at like the large scale, so we can just simply do that. Another tip is to minimize the memory. So a thing with, I guess, C++ programs, or I guess programs in general, is that memory leads indirectly to more time because of the fact that your CPU has like special optimization stuff like caches that can make your algorithm run much, much faster if you use less memory. In particular, if you pick k to be a smaller value, I don't know if you tried smaller values of k, like 100 or 200, that might have helped you. And okay. So these two are kind of the things that I would do. If you still get time limit exceeded, we can look over it. I guess just ask in the CPMSoc Discord, and we can try and figure out what exactly is wrong with the code, or what exactly is slow about the code.